All right, it looks like it's time to start, but there is a, there is a less audience than I expected. So I don't know how to start it from now on. Okay, I'm Hwang, and today I want to share about how we maximize the performance of the HTML5 video in Raspberry Pi 2. So I'm working in the Igalia, which is the open source software consultancy, and I'm working on the WebKit project. And recently, I'm working on optimizing the performance and the memory uses in the Raspberry Pi 2 to play some YouTube TV or etc. So in this talk, I want to share what I did and what our team did to the WebKit to optimize the performance, the HTML5 video. As you can see in this slide, HTML5 video is a simple, it's an old one. Yeah, it's comparably old technology, which replaced the Flash to play a video. But in this scenario, you can see there is some small tux cube are rotating in top right corner of the video. So it is not just playing video. It also handles JavaScript executions and other WebGL, whatever, canvas to give a new experience or rich experience to the video. So we need those kind of stuff in the Raspberry Pi. Anyway, to render this one, those web page before this, in this slide there is a web page. It is also a web page. So this web page is composed by the CSS and JavaScript and HTML. So there is a CSS, how styles are going on, and JavaScript, how renders the WebGL contents, and HTML code to play the HTML5 video. We need an engine to check this source code and make a parsing and layouting and doing whatever to render actual web page. So we call it as a web rendering engine. In this project, we are using the WebKit as a web rendering engine. And so this WebKit is widely used in the PCs, including the Safari, or now it's Chromium forked from the WebKit, so they are using their own web engine anyway. But phones in the iOS, and TVs, and in-vehicle infotainment devices, and smartwatches. So let's see. Samsung released the Tizen smartwatches. So they using the WebKit in the smartwatches. So it's quite incredible. And also in the Raspberry Pi 2. So there is several ports in the WebKit. So for the Mac and for iOS and for EFL, for Tizen, for GTK. So we are focusing in our company, Igalia, are focusing on the GTK port because we are maintainer of the WebKitGTK port in the open source community. So what is the WebKitGTK? So WebKitGTK is a fully featured web engine, so it supports every aspect of the web browser, such as clipboard and whatever preferences. And it is quite useful if you want to implement something like a web-based application. For example, there is an Evolution, which is an email client in the GNOME environment. It uses the WebKit as to render the email. So not only for the browser, it also used in the various applications to adopt web technologies. And also there is Epipany, which is a full web browser for GNOME environment. So it's quite useful for every use cases. And there is another thing, the WebKitForWayland. It is heavily optimized for embedded systems. So we removed some toolkits from the WebKit side. So WebKitForWayland has a much less dependencies compared to WebKitGTK. I don't have to mention about the Chromium because Chromium has a really, really huge dependencies. So that's why Chromium is uses so much memory in embedded systems, and it is really hard to cut down the memory uses. Anyway, so we choose to avoid using the toolkits, so it is quite less functional, but it is quite fast and it is quite lightweight. It is totally focused on the embedded systems with OpenGL. So it is used. So we are using the WebKitForWayland in the Raspberry Pi platform to render the YouTube TV or other STV specific contents. So it is basically full screen contents without any borders or any buttons. There's all of those contents is composed in the web HTML5 stuff. So it does not need any other toolkits such as window managers or GTKs. So it is really lightweight. So before I start to what we did in WebKit and what we did in the video rendering stacks to maximize the performance, I think I should talk about the WebKit. So are you, what's that? Do you know the WebKit, how it works? Is there anybody? Yeah, more or less? Yeah. I think it is the same for me, though. I know more or less. So we need there is a steps for rendering the web engines. Because why I should say about this is WebKit is quite huge and quite heavy operation to render the web page. So we need to parse the HTML code and the CSS code and the JavaScript code and execute and construct the render objects and construct the trees. So that when we have a byte streams from the network stack, we have to tokenizing this and create node trees and DOM trees. After that, we need to create a CSS object model also because we need to calculate the layouts from the CSS styles. So from there is a document object tree from the HTML contents and the CSS object model from the CSS style sheet. And by combining them, we can create the render tree. So render tree, it has which should be rendered and how should be rendered. So from the render tree, we can actually render the web page. So from the render page, we need several layers to render the actual scene. So briefly, it's quite huge. Anyway, briefly, there is a render object, as I explained earlier, quite fast. WebKit, web core itself creates a render object, and then from there, we make layers because let's see the previous examples. Yeah, in this example, you can see several layers. There's a video. Video has itself one single layers, and over then, yes, this rotating cube because it's a little bit small. But anyway, this is a WebGL content, so it has a separate layer, and there is some black boxes which shows current FPS. So this is another layer. So there's several layers in this web page. We need to create these render layers and graphics layers to use GPU to composite the web page. So to utilize the GPU to render the whole scene. Yes. So we create render layer, and from there we create graphics layers, and then we have some platform graphics layer because from this layer we can create several platform-specific graphics layer because WebKit itself has several ports such as Mac and iOS and GTK, so every port has a different approach. to make a real platform graphics layer. And then we use some platform compositor, which uses OpenGL or OpenGL, and actually we draw the whole scene. So this is a whole step, yes, whole step how we render the web page. The problem is, basically, originally it was a single thread operation. It was heavily optimized for single thread. So yeah, it was not a big problem in the desktop situation because we have a quite powerful CPUs in the desktop. So we do not need to optimize. We do not need to make another approaches. But problem is when we are using it in embedded systems, because CPU is quite slow compared to desktop, that makes really hard. That makes really slow whole operations such as layout and parsing and JavaScript executions and rendering. It's quite slow. It was quite slow in the embedded systems because main thread is really busy. If there is a huge JavaScript applications in that web page, sometimes JavaScript core will stop the world to garbage collect. So there is something, performance will be dropped time by time because of the garbage collection. So it's really painful. And another thing is that there's a vsync timing. So when we render the contents, we cannot render directly without waiting anything. We should wait a vsync timing to prevent tearing and whatever splitting, ugly stuff in the display. So we need to wait for vsync. And other than that, we need to adapt many HTML5 technologies, such as HTML5 video and WebGL and HTML5 2D canvas, and many CSS filters and whatever. So it is quite a huge operation. So in best case, if we execute JavaScript really fast and we rasterize everything in the really fast within 16 milliseconds, there's no problem at all. We are all be happy. But problem is if other operations exceed the 16 milliseconds, in that case, frame will be hugely dropped. So this, I make some diagram to describe worst case. As you can see, there's several vsync interrupts in this line. So if we can draw every frame to match with the vsync interrupt, in that case, we can achieve 60 FPS. But in this case, we need to wait the JavaScript execution and layout operations and rendering operations. We should skip one more frame, and then we need to wait next vsync timing. It will waste the main thread. Not only just waiting, it will blocking whole the process in the main thread. So it's a totally horrible scenario. So we can in this scenario, we just can render just 4 frames within this time frame. It's quite horrible, maybe 12 FPS, I don't know, 12 or 20 FPS. It's quite a horrible scenario. So, but luckily in Raspberry Pi 2, yes, we have a quad core. So it is different from the Raspberry Pi itself. Yes, in previous project, we need to think about the CPU power and the memory, and we cannot get advantages using the multiple threads. But from Raspberry Pi 2, yes, there is a quad core. So we can use powerful code, not so powerful, but powerful multi-cores. So why not utilize those CPUs? So first thing we did is split the whole main thread job and compositing job into the dedicated thread. So that we create a dedicated thread to composite the whole contents. And we copied every properties to the compositing thread, so we can do any CSS animations or scrolling or scaling itself without interrupting the main thread. The thing is, the main thread do not have to wait the vsync timing and do not have to consume the time for compositing operations. So it is a big thing. So while garbage collecting, the JavaScript collects the garbages, compositing thread will run itself. So there, in user's perspective of view, there is no delays and there is no, stop the world happened. So there is no Emacs-like things happened in the user perspective of view if we split the compositing thread separately. So what we did is we split the whole the things from the rendering pipeline. We split the platform graphics layer tree into a separate thread. So from the main thread point of view, there is no OpenGLES commands or there's no OpenGLES operations in the main thread. But yes, there is some OpenGLES operations in the WebGL side, but in this case, yeah, there is no OpenGL operations. So main threads do not have to wait the GPU drivers, and compositing will be done in the compositing thread. So there's no big problem. There's no problem to wait the vsync timing in the main thread. To do that, we actually send the commands of state changes, just changes, and that we do not share the layer trees from the main thread with main thread and compositing thread. We do not share. We just create a separate layer trees. Maybe you can think it is a little bit waste of memory, but it is much better to have multiple locks for the layer. For each layers, because we have web core doing huge operations in each layers if there is a style changes or JavaScript. Maybe JavaScript can write down some. JavaScript can include the DOM object in the current DOM tree, or can change the style sheet. In that case, there's a huge changes will be happening in graphics layers. So whenever that happens, if we have a lock in that case, yeah, it's another big problem. So we create separate trees, but it is not a huge memory because it just have the properties such as width, height, or ordering, or colors. Yes, that's all. So there is no big data structures those layers had. So it is not so, yeah, more or less not so big deal, but we can free from the locking operations. So we implemented those things with message passing. So after that, those worst case we already looked at in previous slide. Turns into the new scenario. So we could only render just 4 frames in previous scenario. Just I assume the same execution time for each operation. In that case, we can render almost 8. So it's more or less 60 FPS. We can achieve a 60 FPS. We experimented this scenario several times, and we were quite satisfied about the performance because we could get almost 60 FPS for complicated CSS animations. So it was quite nice. Yeah, it was a quite nice result for us. So in the WebKitGTK, we implemented this not only for WebKitForWayland, but also in the WebKitGTK. So we shared same compositing backend for the WebKitGTK and WebKitForWayland. So we have a dedicated compositing thread. So we just split the big operations from the main thread, and we implement it using the message passing. So there's no big problem with the data. Yeah, there's a thread. In this approach, we make several threads and handling several threads. But there is as a programmer, if we have several threads and we create multiple threads, it became became easily to access of evil, a lot of bugs, but so that's why we try to implement most of the things using the message passing. So we could reduce latencies for scrolling and scaling. I didn't explain about this because it is out of focus, but we can pass user event to the directly compositing thread instead of main thread. So if we scrolling web page or scaling web page, in that case, we just pass those events to the compositing thread first, and compositing thread will scale or scroll the whole web page because it already have all layer trees, so it can do that. And then the event thread will pass the event to the main thread, and main thread will calculate real layout after scaling or scrolling. And then we're going to the compositing thread again, so it renders correctly, renders the updated layout. So in user point of view, in extreme scenario, there can be some problems, like a layer is disappearing at some point or that, but in most cases, there is no big problems. And for user, it is really fluent to scaling or scrolling. So until that, I was talking about the video HTML rendering and compositing. Now it is time to take a look at the video rendering. So for the video rendering, because I'm working on the project to optimize the YouTube TV in the Raspberry Pi 2, so it was a main focus for me to optimize the whole performance and reduce the memory uses in YouTube TV, because we have a restricted hardware and restricted memory. So in WebKitGTK and WebKitForWayland, we are using the GStreamer as a multimedia playback backend. So because we are using the GStreamer, GStreamer itself has a lot of functionality itself. So it has a demuxers, it has streaming, complex audio handling, and whatever, and rich plugins. It's quite easy to use. It is not quite easy for me, but yeah, for GStreamer developers, they said it is quite easy to use. So okay, I'll do it. So it has a quite huge foundation. So we are using the GStreamer, and there is an API, and API is quite stable. So we do not have too much worry about upgrading the GStreamer. So it's another good point. And there is a OpenMAX. So it is a GStreamer OpenMAX plugin. So luckily, there is a Raspberry Pi, they support OpenMAX video decoding specifications. So they can decode H.264 and other codecs using their hardware, decoding hardware, using the EGL images. It's quite well integrated, so we can use that quite easily. But there was some problems, like, yes, there's some problems. There's a source and demuxers, so we can pass just the source, and in that case, demuxer pass the audio streams to the audio decoder, and auto audio sync will play the audio, so there's no big problem. But video decoder had some problem. As I mentioned earlier in GStreamer OpenMAX, GStreamer is quite well implemented, but when we integrate it with GStreamerGL, there's some problems. So there is, let's see, okay. In OpenMAX video decoder, that decodes its contents into the EGL image or CPU buffer. That means when we are using the GStreamerGL, so which uses OpenGL ES or OpenGL to manipulate the video frame, we should upload the texture. Practically, yeah, in theory, we don't have to upload the texture because EGL image itself represents some GPU side buffers. It depends on implementations, but it implies it has already reference in the GPU side, but implementation of the GST-OMX and GStreamerGL was not linked properly at this time, so we need to implement other things. So the thing is, we should, when we use the GST-OMX at first time, it should upload the decoded frame to the texture. So let's see about the 720p video. In that case, almost 3.5 megabytes. If it is RGBA format, yes, we should use more textures, more texture memories. And another thing is can be happened. It is a really bad scenario. It's a worst scenario in that case. So if OpenMAX decode its content using YUV format, color format, in that case, we need to convert it into the RGBA format again by the GL color convert. So we need to consume more memory. And not only consuming more memory, each conversion needs to use the whole CPU. So Raspberry Pi is an embedded device, so we should use whole data buses to the memory. So CPU also will be stored. So that was a big problem. So when we used GST-OMX at first time with the GStreamerGL, almost 10, I could play the YouTube video in almost 12 FPS. It was horrible. Yeah, in 12 FPS, yeah, that was really a horrible situation. So we should polish those stuff to remove those overheads. We implement EGL image memory, which, GSTGL memory EGL, yes. We create a GSTGL memory EGL, which is has the same interface of the GL memory, which is used in the GSTGL. So we implemented a new memory interface for GSTGL and GST-OMX. So we just implemented GSTGL memory EGL, but we can implement another memory wrappers such as DMA buff, which can be used on other platforms, and we can use another. I don't know. Only thing I have to know is I have to implement GST. Yeah, I had to implement GSTGL memory DMA buff. But other than that, I don't know, not yet. Anyway, so by implementing that, we could remove those kind of the color conversion operations and copy operations. So when I had to optimize the performance of the GStreamer, what I learned is GStreamer is a plugin-based library. So you can construct any pipelines by putting elements in the pipeline. What I learned is make pass-through everywhere. Make pass-through. So we still have a GL color convert and GL upload element in our pipeline, but it is a just in case for if the codec is not supported by the GST-OMX, such as I do not know much about those codecs, but if there is some codecs which is not supported by the GST-OMX, in that case, we can use another decoder and then upload those frame to the GL. So it is just in case. So those two elements is just in case to handle exceptional scenario. And if there is no exceptional scenario, such as YouTube TV, we don't have to do anything in the GStreamer side. Just decode the image into the EGL image and use that texture to the compositing. the whole scene. And from there, we implemented another video sync for the GStreamer to integrate with our compositor. So this video sync, what we implemented is creating a platform layer channel and then pass the decoded buffer to the compositor via this channel. So again, it is a message passing. So let's try to minimize the locking operations. And after compositing thread renders the frame, it returns to the buffer pool. So we try to not to wait the compositing thread from the decoding side. So decoding thread will decode as much as possible at the same time. And then compositing thread will consume the buffer one by one. The reason for that is that decoding 1080p video in Raspberry Pi 2 would consume almost 12 milliseconds in the Raspberry Pi 2. So it's quite huge. Yeah, we can do it. We can render it in 60 FPS if we are really lucky. But yeah, it's a 12 milliseconds. It's really huge operation. So we really decoupled those pipeline, the decoding pipeline and compositing thread, and just make some channel dynamically and pass the decoded frame to the compositing thread and free the buffer to the decoding thread. So we just pass the buffers to thread and thread. So that's what we implemented. And this can be also applied to the desktop area, because if we use the GStreamerGL API, yes, there's no big difference. But there's some difference because we didn't optimize the GStreamerGL API with the GStreamerGL yet. So there is some problems. Still, there is some problems while copying the buffers. But my laptop is quite fast, so I can watch YouTube without big problem, even if we have to copy some textures from the GStreamerGL API. But as I mentioned already, and when I'm using the Raspberry Pi 2, yes, we have to clean up all of the stuff in the GStreamer pipeline to remove any possible conversions or unloading or copy operations. So that's what we did in the GStreamer video decoding side. So this is just diagram to show you what happens in multiple threads situations. So the main thread, will, yes, in previous scenario, in main thread will parse the video tag, and it make a HTML5 video element, and then there's a proper attributes. Or if there is an attribute of the autoplay, yes, it will start to play the video. In that case, those play video message will pass to the decoding thread, and the GStreamer will start to consume those sources, file sources or network sources. So it starts to decoding the frame. While then, compositing thread will create initial scene. So before that, main thread would already passed, it passed the whole HTML page and the CSS style sheet. It already created a document object model and CSS object model, and then render object. So we should render it as soon as possible. So previous frame is rendered in compositing thread. While compositing thread renders the previous scene, yes, decoding thread starts to decoding the first frame. And yes, it would handle some color conversions or timing functions and pass the decoded frame to the compositing thread. And compositing thread will return the previous return the previous video frame if it have already, and it will be returned to the buffer pool of the decoding thread. While that, the main thread will handle JavaScript operations if there is another JavaScript operation such as WebGL, or more usable scenario is checking the what's that, AJAX operations, and then receive the tweeters or subtitles and whatever, and try to render subtitles or Twitter responses, and it can create more layers during that time. So it will create those layers and commit those changes to the compositing thread. So compositing thread will render the whole scene with those layer changes and decode the frame. So it renders a single swap buffer with a new video frame and with a new changed layers. So it will, there is no, we try to make, not to make many locks, but there is some problems. I should say there is some problems like when we handle the timing, but most of the times it works well, and most of the times it utilizes the whole process really well. So this is a more complicated scenario with 2D canvas rasterization. If there is an accelerated 2D canvas, in that case, we need to execute. We can execute a separate thread for the 2D rendering, 2D canvas rendering. So in that case, it will be more complicated scenario. But even in this graph, we implemented those framework to use message passing. So main thread and decoding thread and canvas thread will just pass the final frame to the compositing thread, and compositing thread will render it as soon as possible when it can. So if there is no vsync timing, if it passed the vsync timing, it will render the next vsync timing. So by then that, we could minimize the locking time by the vsync to other threads. So the vsync will be considered in the compositing thread only, and the compositing thread will gather the vsync timing from the compositor or GPU drivers. So there is no big wasting time from the two-way GL swap buffer calls. So that's what we did to maximize the performance of those rendering stacks, including the video and canvas calls. So this is the test result in the Raspberry Pi 2. So we target to 720p and 1080p because Raspberry Pi 2 supports those resolutions. So for the HTML5 video playback, 30 FPS, it's quite fluent. If it's most of video is targeted for 29 point whatever FPS. So anyway, 30 FPS is quite usable. But I was trying to improve the performance of the user interface while playing the video. You can see when we using the YouTube video, you can show up the controls or other interfaces or other, not in the YouTube TV, but as far as I remember, there is some demo cases with a wonderful user interface with Twitter or chatting with a video, whatever. I do not know why, but so I'm trying to implement more content-rich scenarios. So that's why I put those WebGL and HTML5 video to check the performance. So if we play 720p video with a WebGL contents, it shows 40 to 50 FPS. It has some vibrations because it still have ghost copies. So the thing is, in the Raspberry Pi, natively Raspberry Pi decodes the video, OpenMAX decodes the video via 2 YUV color space. And to render the actual video frame, we need RGBA. So yes, the Raspberry Pi 2 GPU will convert the YUV to RGBA automatically, but yeah, not magically. So automatically means it consumes the GPU resource inside of the GPU driver. So that makes some problems over the performance. But yes, and anyway, we could reduce the memory consumptions, and we reduced the whole. We could reduce the whole conversion operations during the pipeline, and we could remove the vsync timing from the main thread, so we could improve the whole performance. And thank you. And you can see the demonstrations of the Raspberry Pi 2 and WebKitForWayland and other embedded boards in the demonstration hall. So, and if you have any more further questions about that, you can feel free just ask us about your questions about or whatever. Yeah, thank you. And is there any questions? Yes. Excuse me? Did you have trouble syncing up the audio? So. Or even the text caching? So yeah. For audio, we had some problems at some point, audio and video syncing, right? Yeah, so it is hard to make exact timing if we don't have a resource enough. So in this scenario, in this handling timing, yes, it is an important thing as far as I know, because GStreamer will pass the frame as much as possible at exact timing. But if you have, it is a limited resources, in that case, it can be delayed unexpectedly. So that's why, we faced something, sometimes we faced not synchronous audio and video. So after polishing those pipelines, I didn't face that so much. Yeah, it's getting better. And another tip is you can request the frame from the GStreamer a little bit earlier than the exact timing, and you can manage it yourself to match the timing. So if you have a separate compositing thread or separate compositing component, like us, in that case, you can implement it yours to match the timing with audio and video. Also, you can drop yourself the frame. I think I suggest you to use those framework. I forgot the signals, but properties, but you can request the GStreamer to get a frame earlier. Our WebKitForWayland using the Wayland subsurface, a subcompositor, right? A subcompositor. So, but we do not play the video in the Wayland compositor. So Wayland is we play the video in the texture, not a compositor buffer. So because we should able to apply video, CSS styles or opacities and CSS filters and whatever to the video element. So we didn't try that. We just treat it as a single texture and single platform. Yes. Yes. Thank you. So compositor, it is in the WebKit side, we use the OpenGL. So we wrote our compositor. So it is a text mapper and threaded compositor. So it is in the WebKit side. And window management side, system side, it depends on the situation. WebKitForWayland, we are using the Wayland as the name says. And WebKitGTK, we can apply it X window and wherever. And nowadays we are trying to use WebKitGTK in the macOS too. Yes, finally, Wayland composite the result to the screen. So our current setup is rendering the contents to the Wayland Wayland buffer, and Wayland would composite those buffers to the screen, actual screen. Okay, so it is done. So if you have a further question, please meet us in the booth. There's Igalia. Yeah, thank you.